Good afternoon, everybody. Well, artificial intelligence is all over the place today, not only in broadcast, but mainly in a lot of other industries. If you, for instance, think of what Google is doing with the Chinese The Go game, an artificially intelligence-based system was capable of beating the world's best players. If we think of image recognition algorithms, neural networks are capable of detecting, of knowing what's inside an image, actually better than humans do from time to time. If we think of automatic driving cars, all of these new technologies that will fundamentally change our world are based on artificial intelligence. So obviously then the question is, can artificial intelligence also mean something for broadcast? And the answer is clearly yes. But before explaining why the heck would we need artificial intelligence, let's have a deeper look into what does a new live production mean today. Actually, if you compare it to, let's say, a few years ago, more and more and more work is needed. Because users expect to have the content on more devices. They expect personalized content. They expect the content on different platforms. And that's just the user's perspective. The content itself is also being more and more enriched. The content is enriched with in-game statistics, biometric data from the players, as we've heard before. So you would say, so far so good. More work to do. This looks great for the broadcast industry. Unfortunately, all of this has to be done on much tighter budgets. So then, obviously, what is a possible solution is if you think of automation. Can we automate a live broadcast production? Let's hope so. But unfortunately, what we learned is that the traditional techniques that have been used very successfully, by the way, in other industries, let's say like techniques that, for instance, maybe 20 years ago, have been used to do license plate detection, all of that doesn't really work in broadcast. And the reason for that is that human operators in broadcast, they're not just applying a mathematical formula. They are doing something creative. They're making a story. They're bringing a real experience when they're doing their job. So actually, they have this artistic touch. And that's the problem, because traditional techniques cannot cope, cannot copy, cannot replicate the creativity that human beings have. But that's where artificial intelligence comes into the picture, because artificial intelligence will actually allow us to copy that creativity, to mimic the creative storytelling, the artistic touch of human operators. For that, we use a new class of technologies, neural networks, machine learning. And those class of technologies have been used to actually solve the most challenging problems. One of the fundamental aspects of these neural networks and machine learning approaches is that you don't explicitly program the algorithm. You are not devising, let's say, some kind of flow chart that says, now do this, then look for this corner, then look for the ball, then look for the player. These machine learning techniques, they work based on learning. You just feed a large amount of examples to a neural network, and then it will automatically learn by itself and apply what it has learned on new examples. Just think of if you have a huge amount of images. So on some of the images there is a car, on others there is not a car, and you want to have a system that finds out on which image there is a car and on which there is not a car. How such a system then works is we feed it with a large amount of images, with cars and without cars, but we also tell, obviously, the correct answer. Where is the car and where not? And then after the training phase, the neural network, if you give it a new image, will tell you whether or not there was a car in that image. The basic element of a neural network is what's called a neuron. That's actually the mathematical representation, a pretty simple thing. It has some inputs. There are some weights applied to the input. You sum all of that. And if that sum is larger than a threshold, the neuron is set to fire. Basically what it does, it will send a signal to all or to its neighboring neurons. One single neuron doesn't do a lot, actually. Actually, we need a complete network of neurons. And just to make life mathematically a bit easier, the neurons are generally organized in what's called layers. The first layer is the input layer. In our example of images with cars and without cars, that means that all the pixels of the image, you feed it into the input layer. Then you have the output layer. The output layer will give you the result, the answer. In the case of the car example, it's pretty simple. It's yes or no. But it can be much more complex. And then you have a lot of layers in between, hidden layers or intermediate layers, and all of them compose the neural network. For those of you who've heard about deep learning simply means that you have a whole array of hidden layers, not just one or two, but maybe 10 or 20 or even more. Just for reference, the human brain also works with neurons, biological neurons, that sort of work according to the same principle. But to give you an idea, the human brain, at least what I read on Wikipedia, is supposed to have between 85 and 100 billion neurons. Each neuron can fire, is in touch with 10,000 of its neighboring neurons. So that's huge. The neural networks that we use today are not of the scale of the human brain. But still, they can do some quite interesting stuff. ImageNet is a very large image database, and every year they organize a contest. They organize a contest for the algorithm that can best identify what is on these images. And you see, over the years, we started with a very high error rate. 2015, the error rate is low. We are below that red line. That red line is sort of what the average human will do. So the algorithm behaves at least at par with a human. And this has been achieved by these deep learning networks. You see there, we started with shallow, a few layers, 8, 19, 22, 150. So the more net layers that you have, the more complex that your network is, obviously the more things that it can do. But such a network, such a neural network with all these layers, actually then it means we are referring to a network that has millions of parameters to tune. You're not going to do that by hand. And that's, again, where machine learning kicks in. So machine learning just works like humans sort of do. You have examples, and you learn by example. So we have a first example. We know what the ideal outcome is. The neural network has some initial parameters. We feed this first example to the neural network. It will generate some output. We compare that output with the ideal output. For the first example, it will most likely not be OK, but then we update the parameters of the network. And that will repeat for every possible example that we have. After some time, the network will converge. I mean, the parameters will stabilize. And then we have our final model. And this final model, so now the learning phase finished, this final model is then applied to new images that will generate the output by mimicking, by copying from the examples that has been given. And by that, let's say, specific nature of how neural networks work, we are capable of replicating, copying, mimicking the creative, the artistic behavior of human beings. So that gives quite some opportunities. Because of that, in the broadcast, we can use artificial intelligence to produce more, to produce faster, to produce better, while still allowing operators to concentrate on their core activity, which is being even more creative. And OK, for that reason, EVS is gradually will introduce artificial intelligence techniques in its products. In the few coming slides, I will explain some of the examples that we developed in the innovation department. Our first example is on automatic framing. Automatic framing is the process where you start from a full HD image of the soccer game, and by applying an algorithm by a machine, you automatically, and obviously in real time, we're alive, creating a cutout portion of that image. There are various reasons to do that. One reason is if you want to publish on social media, some of the social media require a different aspect ratio. Another interesting reason is for so-called mobile-first feed. That is, if you want to see the game on a mobile screen, looking at this full-size image on a very small screen will not be so appealing because all the players will maybe 1 or 2 millimeters in height. On the mobile device, you really want to see the heat of the action. A third reason why this kind of technology is applied is if you have, let's say, not a moving camera, but a fixed camera, a 4K fixed camera, and you want to cut out an HD view to mimic the behavior of the cameraman that's following the action. Here, an algorithm will follow the action. First, we tried to do that with, let's say, the standard approach that would be try to find the ball in the image, follow the ball, follow this or that. We tried it, doesn't work. Technically, in some cases, it does work, but the quality of the output is not high enough. I mean, it's simply not pleasant to see. So that's why here we adopted artificial intelligence. We learned the algorithm, actually a huge amount of soccer games. We identified a human being, identified where is the core of the action happening. The network learned, and then from there on, automatically, for any new soccer game, we will find where the core of the action is. And then with that information, we can do automatic framing. We could do some other stuff as well based on eyeball tracking and the like. The second example that we developed is automatic direction. In an important soccer game, Karel already mentioned it, it's a Champions League, we're referring to 40-odd cameras around the field. Today, the director decides at every given moment which of these 40-odd cameras is put on air. That's a tedious job. And we need today a director to do that just because he brings his creativity and so on. We took on the challenge to actually replace that by a system. So we developed an algorithm based on artificial intelligence that will, and then it's the algorithm that will select the camera out of these 40-odd cameras. We developed a prototype, and actually we've shown the results to quite a large number of people. So we showed on one hand the outcome, the result of the algorithm. On the other hand, we showed the original work of the director. In many cases, people were not capable of telling who did what. Who was the human being, who was the director. In all fairness, the directors that saw it are capable of identifying which one was made by a director and which one was made by the system, because they even better, obviously, than the algorithm know how they would do it. And the last example that we developed is this, again, by using neural networks, is this automatic geometric transformation. What we do there, again, all what we're doing is real time. We take image by image coming from the original camera. We calibrate the camera. Calibrating the camera, that means that image by image, we know the transformation between this distorted view in perspective and the ideal 2D view of a soccer field in this case. Today, this is generally done manually, and the camera isn't supposed to move a lot. Here, we just do it based on the images, image by image. What we can do then, obviously, is in that middle view, which is the perfect rectangular 2D view of the soccer field, you can start drawing lines. You can overlay objects on there, and you can overlay them, you can draw them, well, perfectly parallel aligned if it were an offside line, or a circular image of a logo, and so on. And then by applying the reverse transformation, we show these overlaid graphics, again, in the original camera image with the perfect perspective view as seen by the camera. So that's just, in a nutshell, 3 things that we have developed. We're doing more. But these 3, if you want to know more, we have a stand. Just come and pass by if you want to have more information. So artificial intelligence, neural network, all the stuff looks great. But it's not as simple as just going to the math store and ordering, give me a neural network. What we found out is that it really requires a detailed understanding of and the broadcast industry and artificial intelligence technologies to come up with a good result. And the reason for that is that you need to know the broadcast industry to understand, OK, what's worth automating? How are operators actually working? What does the audience want to see? And you need to be able to translate that choosing the right technologies, because there are a zillion of artificial intelligence technologies, and some are more suited than others to solve a given problem. And the most challenging part in machine learning is actually, I told you, you need to have a large set of training data, a large set of examples. For the automatic framing case that I explained, actually, we went over quite a number of soccer games and manually indicated on each image 50 ones per second where the algorithm had to look at. So there is quite some preparation work to be done. So you won't do that just overnight. If there are questions. No.
I propose that you keep them until the end, because then I will ask everybody on the stage and we can kind of debate around this. Thanks a lot, Johan, Vounckx.